Okay, now that we know a little bit more about the quantum mechanical model, we want to know, how do the electron spots get filled up with electrons? Okay, first I'll introduce you to the Aufbau diagram. An Aufbau diagram can show all the possible spots for electrons. You have one row for each energy level, so there's your first energy level, second, third, fourth, and so on. And then on each row, you put boxes to represent subshells and orientations of those subshells that are at that energy level. So for your first energy level, you put one box to represent the one orientation of the S subshell. And you put a 1s next to it to signify that it is the S subshell of the first energy level. And then for your second energy level, you'll have 2s and then 2p. And this entire clump of 3 boxes represents the 2p subshell. And each of the 3 boxes in the clump represents one of the 3 orientations of the 2p subshell. Okay, for your third energy level, you have 3s, 3p, and then 3d, with 5 boxes in the 3d clump to represent the 5 orientations of the 3d subshell. And then for your fourth energy level, you have 4s, 4p, 4d, and then 4f, with 7 boxes in the 4f clump or 4f subshell to represent the 7 orientations of the 4f subshell. And you keep doing this pattern for successive energy levels. Okay, to help you remember this notation, I'll mark this thing up. This entire clump represents one subshell. In this case, it's the D subshell of the third energy level. And each box within the clump represents one orientation of that subshell. Okay, here are the rules that we use to fill up this Aufbau diagram with electrons. There's the Aufbau principle. Electrons fill the place with the lowest energy state first. What does this mean? Well, they like to fill the place with the lowest energy state first. They want to find the place with the lowest energy. That's what they want. That's what electrons want. This typically means that they fill the energy levels in the order of 1, and then 2, and then 3, and so on with increasing numbers. And then they fill the subshells within each energy level in the order of S, P, D, and then F. Of course, if an energy level just has 2 subshells, say energy level 2 has the S subshell and then a P subshell, there wouldn't be any D or F subshells to fill after that, so it would just go on to the third energy level subshells. Then you have your Pauli exclusion principle. Each orientation can hold from 0 to 2 electrons. This means that the max number of electrons for an orientation is 2 electrons. And if an orientation does get up to its maximum of 2 electrons, then those 2 electrons must have opposite spins. What does this mean? Well, let's use the example of helium, which has 2 electrons in its neutral state. Let's put down our box, 1s, because that's the lowest energy level, and that's the lowest energy state place that the electron can go. And so then we want to fill that first. Here's our notation. An up arrow or a down arrow either can represent 1 electron. One box then can have a max of 2 electrons in it because each orientation has a max of 2 electrons. So an up arrow represents a plus 1/2 spin electron, and a down arrow represents a minus 1/2 spin electron. You don't have to do any math or fancy calculations with those numbers. They just indicate that the electrons have opposite spins. So first we put an up arrow, and then we can't have the same spin arrow in the same orientation, so we have to put a down arrow, and that satisfies the 2 electrons of helium, so there we go. And then we have Hund's rule. When you're filling a subshell that has more than one orientation, that is the P, D, and F subshells, not the S subshell, which only has one orientation. First you fill each orientation of the subshell with 1 plus 1/2 spin electron. Only after all the orientations of the subshell have 1 electron, only then can you go back and add a second electron. Of course, a minus 1/2 spin so that they have opposite spins in each orientation. But only then can you add another electron, double up in each I put orbital there. I meant orientation. Okay, let's do an example. Oxygen. In its neutral state, it has 8 electrons. Let's put down our boxes, and if we happen to need more, we can always draw more. Okay, first an up arrow to represent a +1/2 spin in the 1s subshell, the lowest place it can go first. And then a down arrow for a -1/2 spin, because 2 electrons in the same orientation must have opposite spins. And then we go on to the 2s subshell. Oh, I wanted to show you, these are what are called electron configurations. They show for any atom it's basically a list of all the electrons in the atom and where they can be found. So in here, 1s with superscript 2. That means that at the first energy level, in the s subshell of the first energy level, there are 2 electrons. Okay, now we can move on to the 2s subshell. Have an up electron and then a -1/2 spin electron, and then our electron configuration notation. And then with the 2p subshell, first we fill each orientation with 1 +1/2 spin electron. And then, only then, can we go back and double up with -1/2 spin electrons. It looks like that we have gotten 8 electrons, so that makes this oxygen, which is what we wanted. And then we just write the electron configuration, finish it up, and there we go. 2p4. That means the p subshell of the second energy level has 4 electrons in it. Another way to write the electron configuration notation is to put the noble gas of the period that comes before the atom that you're trying to write the configuration for, to represent all the filled subshells up to that point. And then after that, you can put the additional filled subshells. So in this case, it's helium, and then after helium, you fill the 2s subshell and then the 2p subshell, and you put with 4 electrons. Remember, this is just notation. You don't have any variables. I know it might look like that, but no variables, no exponents, no multiplying, none of that, so don't be scared. Okay, let's do another example. Iron, which has 26 electrons in its neutral state. Let's write our boxes, and remember we can write more if needed. Fill our 1s subshell, and write our electron configuration. 2s, 2p, first do up, first do +1/2 spin electrons, 1 to each orientation, and then double up, and then 3s, 3p, and then we do 4s after 3p, because the 4s subshell just happens to have a little bit lower energy than the 3d subshell. This is an exception to the rule. And then after the 4s, we can go and fill the 3d subshell, and just until we get 26 electrons, which will be iron. And another way to write the electron configuration for this would be with the noble gas argon, which is in the period that comes before the period that iron is in. So we write argon, and then we write the subshells after argon that get filled up to make iron. Okay, we have discovered that there are some exceptions to that expected order of filling. Here is the actual order: 1s, 2s, 2p, 3s subshell, 3p, 4s, and the 4s comes before the 3d, and then 4p, 5s, and then the 5s comes before the 4d, and then you get your 4d, 5p, 6s, and then your 5p and 6s, they come before the 4f, and then 5d, 6p, 7s, and your 6p and 7s will come before your 5f, and then you have your 6d and 7p, and that's pretty much all you need for the known elements. Okay, you're like, probably, this seems pretty daunting to remember this big order, and there's no one rule that'll help you remember it easily. So we remember this order by writing the subshells by their energy levels in rows like this. And then we draw arrows through it, and the order that our arrows hit the subshells is the order that the electrons fill the subshells. Easy, right? So 1s, 2s, 2p, 3s. Remember the arrows are going down and then left. 3p and then 4s, 3d and then 4p and then 5s, 4d and then 5p and then 6s, 4f and then 5d and then 6p and then 7s, and then 5f and 6d and then 7p. Okay, I think we have time for one more example. Let's do germanium. And it has 32 electrons in its neutral state. So I think we get the idea of the Aufbau diagram, so let's not draw one for this. Okay, let's just do the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2, or you can write it as argon, 4s2, 3d10, 4p2. Now you see here, the 3p subshell has come before the 4s subshell, and then you continue on with your 3d subshell, and then comes your 4p subshell. Okay, I hope this video has been helpful to you. I know it's kind of a lot to take in at once, but yeah, I really hope this video has been helpful to you. Goodbye.